Till now we have come across several convection diffusion discretization schemes. For example, the central difference scheme, the upwinding scheme, the exponential scheme and the hybrid scheme. Now we have seen that in the hybrid scheme it is very much faithful in terms of a qualitative representation of the exponential behavior, but it switches off the diffusion term a bit quickly. So beyond Peclet number equal to 2 or mod of Peclet number equal to 2, so to say, by considering both the positive and the negative sign, AE by DE becomes equal to 0. In reality the term is switched off to 0 for a Peclet number which is somewhat greater than that. To accommodate for that, what one can do is one can still avoid the exponential calculation. The exact exponential calculation will give that corresponding trend, but as we have seen that the exponential calculation is computationally expensive. So instead of doing the exponential calculation, one can make a curve fitting of the exponential behavior through a power law type of formulation, and that is known as a power law scheme. So let us just write the corresponding discretized version of the power law. So it is this power law is described as follows: AE by D is equal to minus PE for P tends to minus infinity, or even between minus infinity to a negative number which is large enough, minus 10, is 1 minus 0.1 Peclet number to the power 0.5 for Peclet number between 0 to 10 and is equal to 0 for Peclet number greater than 10. So instead of considering Peclet number equal to 2 as a switching of parameter, Peclet number equal to 10 is considered as a switching of parameter. The exponential behavior is such that it dies down to 0 for the corresponding argument tending to 10 in terms of magnitude. So now where from these formulae come? These are essentially curve fitting of the exponential behavior. So if you try to represent the exponential behavior in the form 1 plus a into Peclet number to the power b, then by using method of least squares one can find a equal to 0.1 and b equal to 5, not exactly these but very close to these ones. So that is a numerical exercise. We will not go into that numerical exercise because our objective is to understand where from it comes and to make use of it and to know that why it is important. So we have to remember that exponential scheme would have otherwise worked fine, but because exponential calculation is expensive we are going for alternative. Hybrid is not a bad alternative, but it switches off AE by DE to 0 at Peclet number equal to 2. We want to switch it off to a larger Peclet number value, say 10, and that is done in conjunction with a power law formulation where basically you do not have to calculate exponential behavior, it is just to the power 5 means 5 times the multiplication, that is the whole calculation, which is computationally much more inexpensive than an exponential calculation. So that is the motivation behind this power law scheme. Now you can combine all these to write a single expression AE by DE is equal to max of 0 to 1 minus 0.1 mod of p to the power 0.5 plus max 0 minus p e. So, what we can see, let us consider an example when you have this range that is between minus infinity to minus 10, this part will only be important, this part this will be 0. So, it will be minus of p 0.1 mod of p to the power 5. Okay. Yes, whole to the power of 5, right. Whole to the power of 5. So, what we can see from here is that if you go for different ranges, all the different ranges can be accommodated through this common formula. For example, if you consider the range of between minus 10 to 0. So, between minus 10 to 0 mod of Peclet number is minus Peclet number and this term will dominate over this term. So, this is like the hybrid scheme where you replace the linear part by this power part, it is almost like that, and max of 0 and minus p is minus p. So, this minus p for the Peclet number between minus 10 to 0. Between 0 to 10 you have max of 0 and minus p is 0 and therefore and max of these two is this one. So, 1 minus 0.1 p to the power 5, and for Peclet number greater than 10 both of these have max 0. So, the net result is 0. Therefore, all these ranges can be summed up by this single integrated formula. Now, what we want to see next is something as follows. What we want to see next is that how we can utilize the understanding that we have developed so far for calculation of the coefficients in a generalized framework. So, till now we have considered several different schemes and the schemes different schemes have given rise to different coefficients. Now, what we want to see is that if you have a generalized description of the corresponding convection diffusion scheme, then that generalized description how it can be utilized to represent all the schemes, but in a generic form, not in the specific forms, that is no different formula for a central difference scheme or an upwinding scheme or a power law scheme, but a unified formula or formulation where expressions of different terms may be different for different schemes, but the formulation is general and the formulation is not different for different schemes. So, that we call as a generalized formulation, generalized convection diffusion formulation. In the generalized convection diffusion formulation, what we want to consider that there are two grid points I and I plus 1, there is an interface and there is a flux through the interface. We want to represent this flux in terms of the values of the variable at the grid points by considering both advection flux and diffusion flux, which is something that is consistent with any of the convection diffusion formulations. So, remember that J is rho u phi minus gamma d phi dx. To make it generic, what we will do, we will consider a non-dimensional j. So, we will consider j star as some j by gamma by delta. You can see that j has rho u phi, that means f into phi. We have to divide f by d to get the Peclet number. So, that d is gamma by delta, some gamma diffusion coefficient by some length scale. So, this becomes rho u by gamma by delta phi minus gamma d phi, or gamma is cancelled. So, d phi d x by delta. So, this is Peclet number into phi minus d phi d x by delta. So, clearly the first term is the advection flux non-dimensional, second term is the diffusion flux non-dimensional. Now, if you consider j star advection, the advection flux is proportional to phi. That means we can say that the advection flux is proportional to the value of phi at the interface, to be more specific. Now, phi at an interface may be expressed in terms of phi at I and phi at I plus 1, depending on the scheme that you are using. It will be some weighted average of phi I and phi I plus 1, no matter whatever is the scheme you use, you dump the effect of the interface as a weighted function of phi I and phi I plus 1. If it is a central difference scheme, it is half, otherwise you can have different weights. So, this is, you can write alpha into phi I plus one minus alpha into phi I plus 1. Okay. Where alpha is that weighting parameter. J star diffusion, we have seen that the diffusion flux is proportional to the negative of the gradient of phi. That means essentially the difference in phi between the points I and I plus 1. So, it is like beta into phi I minus phi I plus 1, where beta is another coefficient, and the j star total is equal to sum of these two. So, you can see that it is nothing but some constant into phi I minus some constant into phi I plus 1. These constants we give the name b and a, where b and a both are functions of Peclet number, because b and a will contain alpha and alpha contains Peclet number. So, b and a are not absolute constants, but these are parameterized functions of the Peclet number, that we must remember. So, every time we will not write b as a function of Peclet number or a as a function of Peclet number, but we will keep in mind always that b and a are functions of Peclet number. So, you can find out what is b. For example, b is p alpha plus beta and a is beta minus p into 1 minus alpha, by comparing these expressions. Now, once we express these in terms of b and a, no more alpha beta, these are important. Now, everything we will be expressing in terms of b and a. Now, this relationship should be satisfied even in very limiting cases. So, what are the limiting cases that we can consider? Let us consider a limiting case when phi I equal to phi I plus 1. Then what is J star? J star only will be J star advection. Diffusion is 0 and J star advection phi I equal to phi I plus 1 means it will be P phi I. So, it is P phi I is equal to P phi I plus 1. Also from the general formula it will be B minus A into phi I or B minus A into phi I plus 1. So, by comparing these expressions we can write B minus A is equal to Peclet number. This is a very important relationship between A and B. No matter whatever is B and whatever is A, their difference is always the Peclet number. That is the first thing. Next is let us try to see that what happens if we alter the flow direction. If we alter the flow direction, before altering the flow direction, so effect of alteration of flow direction. If all the values are the same, what you expect is J star will be reversed because of reversing the flow direction. So, B of P minus B of, now we are writing as a function of P because on reversal of flow direction B of P becomes B of minus P, Peclet number becomes minus P, only reversing the flow direction but not the magnitude, and all other quantities are remaining the same. So, B of P phi I minus A of P phi I plus 1. So, this will be negative of the transport with the reversed direction. So, with the reverse direction now B P will become minus P, in place of phi I it will be phi I plus 1 because now the transport is from I plus 1 to I. Remember when you are writing B phi I minus A phi I plus 1, transport is from I to I plus 1. Now if you reverse the flow, transport is from I plus 1 to I. So B of minus P into phi I plus 1 minus A of minus P into phi I. So if you compare both sides, you will get B of P is equal to A of minus P and A of P is equal to B of minus P. So this is another set of interesting relationship between A and B. With these relationships, let us now try to see that how we can make a plot of A and B. We also have to remember that what is the relationship between this capital A, capital B and our various coefficients AP, AE, AW, which have been defined for the dimensional form of the corresponding discretized equations. So if you write or if you discretize your equation by considering these grid points, you have J star E equal to J star W. So J star E is B phi P. So B of PE phi P minus A PE phi E. This is J E star, and what is JW star? So remember, this Peclet number is based on which length? Distance between P and E, that is delta XC, that is the delta length scale that was used for the general description between I and I plus 1. Here I is P and I plus 1 is E. Similarly, when you consider JW star, so then what will be the corresponding length scale for Peclet number? Delta XW. So it will become PW, where PW is the Peclet number based on delta XW. PW into phi W minus A PW into phi P. So BPE plus APW phi P is equal to APE phi E plus BPW phi W. This is the dimensionless form. Dimensional form, AP phi P is equal to AE phi E plus AW phi W. So which term comes from which? This term, these two terms are equivalent, only the dimensions are different. These two terms are equivalent, only the dimensions are different. And how you can convert one to the other? Remember, when you had AE, let us consider the central difference scheme for example. So you had AE by DE is equal to 1 minus P, P by 2. What it was? 1 minus P by 2. So you can see that AE equal to DE minus FE by 2. This is the example central difference scheme. So you can convert AE to a dimensionless form by dividing it by DE, then it becomes 1 minus PE by 2. So parametric function of Peclet number. So from here what we can conclude? We can conclude that A is nothing but AE by D. Similar terms, only dimensions are not matching, one is dimensionless, another is a dimensional function. So you can convert one to the other by dividing AE by D to get A of Peclet number, function of P, Peclet number based on delta XC. Similarly, B of PW is equal to AW by DW. So that is how you can relate those coefficients with this A and B. So since we have studied different coefficients, it is possible to have an expression of A and B for different cases, and you can make a summary of that. So for example, you can consider a scheme central difference. If you consider a central difference scheme, this is equal to 1 minus PE by 2. Upwind scheme, what was AE by D 1 plus max minus p 0 exponential scheme p by e to the power p minus 1. Just check whether these are all right. We have derived all these earlier. Hybrid scheme max minus p 1 minus p by 2 0 and the power law scheme which we have dealt today max 0 1 minus 0.1 mod p to the power 5 plus max 0 minus p. Similarly, you can write expressions for capital B which we are not writing here, but it is possible to write in this way. Just to see qualitatively how you can have a variation of A and B, let us make a plot of A and B as a function of Peclet number corresponding to the exponential scheme. So, let us plot p by e to the power p minus 1. We have seen that plot will correspond to a behavior like this. This we have already seen through our previous experience with the exponential scheme. So, we are considering an example of exponential scheme. So, this is A. Then you have to remember that B minus A is Peclet number. So, what we are plotting here? We are plotting for A as p by e to the power p minus 1. So, B is equal to this plus p. When this tends to 0, B tends to p. So, it will be something like this. When Peclet number equal to 0, both A and B are 0 1. In that limit, because A is 1 and B is A plus P. So, 1 plus 0 is 0 1. Then when you consider the limit as P tends to minus infinity, when P tends to minus infinity, B is equal to P plus A. So, when P tends to minus infinity, A was tending to minus P, that we have seen earlier. So, that minus P plus P, that means it will tend to 0. So, you can see that if you draw this properly, these are sort of like reflections of one with respect to the other. So, this is B of P, and the difference between these two for any particular P is P itself. And why these are sort of reflections of one with respect to the other? Because we have seen B of minus P is equal to A of P. So, you have B of minus P, say this is minus P. So, this is B of minus P, this is same as A of P, or here is the other way, it is A of minus P in this graph. So, A of minus P is same as B of P. Similarly, it can be shown, it can be seen from the graph that B of minus P is equal to A of P. So, if you consider B of minus P, this is B of minus P and this is A of P. So, all the important characteristics B minus A equal to P, B of minus P equal to A of P and A of minus P equal to B of P are evident from this sketch. Next, what we will do is we will try to generalize it further. We have written it in terms of the Peclet numbers, but it is more general to write it in terms of mod of Peclet number, because the Peclet number can change from P to minus P if the flow direction is changed, but if the flow strength remains the same then mod of Peclet number remains unaltered. So, if we know the result for a particular flow strength, we can apply it or we can extrapolate it for different types of cases by using the information on the coefficient value based on mod of Peclet number. So, that we will do next. So, our objective is to obtain relationships between A of P and A of mod P. When P is greater than 0, A of P is equal to A of mod P, right, there is no difference because mod P equal to P. Now, we can also write that B P minus A P is equal to P and B of P is A of minus P. So, A of minus P minus A of P equal to P, that means A of P is equal to A of minus P minus P. So, when P less than 0, you can write A of P is equal to A of mod P minus P, because mod P is equal to minus P for P less than 0. Now, let us try to combine these two. If you combine these two, then you can write A of P is equal to A of mod P plus max minus P 0. Okay. Because out of minus P and 0, you have 0 as max when P is greater than 0 and minus P as max when P is less than 0. So, it covers both of these cases. So, this is a very important relationship between A of P and A of mod P. Similarly, let us try to obtain expressions for B. So, B of P is equal to A of minus P. that means if p is less than 0, b of p is equal to a of mod p. On the other hand, you have b of p is equal to a of p plus p, that is also true. So that means you can say if p is greater than 0, b of p is equal to a of mod p plus p, because mod p equal to p for p greater than 0. So you can combine these two, one for p less than 0, another for p greater than 0, and say that b of p is equal to a of mod p plus max p 0. Okay. So it is possible to write a of p and b of p as a function of a of mod p alone. So a of mod p is the sole important function, because if you know a of mod p, you can write a of p and b of p both without calculating them separately in a difficult way by straightforward use of the expression of a of mod p. So that is a very important consideration, and mod p, a of mod p is important because it is something that you can calculate irrespective of the flow direction in the same way. So it does not matter whether mod p equal to plus 5 or minus 5, in either case a of mod p will remain the same. So let us try to calculate a of mod p for these different schemes and try to express those in terms of mod p. Calculations for a of mod p. First let us consider the central difference scheme. So a of mod p is equal to a of p minus max minus p 0. What was the formula? A of p was a of mod p plus max minus p 0. So that plus comes in this side. Okay. So when p is greater than 0, a of mod p equal to 1 minus p by 2, right, max of minus p and 0 is 0. When p is less than 0, a of mod p is equal to 1 minus p by 2 plus p. So 1 plus p by 2. This can be written as 1 minus mod p by 2. This is also 1 minus mod p by 2. So you can see that in an interesting way, what we see is that no matter whatever is the Peclet number, the general a of mod p is 1 minus mod p by 2 for the central difference scheme. Then upwind, this is perhaps the easiest. So, A of mod p is equal to 1 plus max minus p 0 minus max minus p 0. So, it is equal to 1, does not matter whatever is the range, it is equal to 1. Then exponential scheme. When p greater than 0, A of mod p is equal to p by e to the power p minus 1. So, mod p by e to the power mod p minus 1, because mod p equal to p when p greater than 0. When p less than 0, A of mod p is equal to p by e to the power p minus 1 minus max of minus p 0. So, plus p. So, p plus p to the power p minus p by e to the power p minus 1, divide both the numerator and denominator by e to the power p. If you do that, it will become p minus p by e to the power minus p minus 1. Okay. So, this is nothing but equal to mod p by e to the power mod p minus 1, because mod p is minus p when p is less than 0. So, for the exponential scheme, the general A of mod p is mod p by e to the power mod p minus 1. Okay. Next, let us consider the hybrid scheme. In the hybrid scheme, we have how many different ranges? One is between minus infinity to minus 2, another minus 2 to 2, another is greater than 2. Here the range of minus 2 to 2 also we have to divide into two parts. One is minus 2 to 0, another 0 to 2, because mod of Peclet number is different in these two regimes. One, because in one case Peclet number is less than 0, and another case the Peclet number is greater than 0. So, let us consider first the range minus infinity to minus 2. So, in the range of minus infinity to minus 2, A is minus p, max of these three is minus p. Okay. So, minus p, so A of mod p equal to minus p minus max minus p 0. So, minus p plus p, that is equal to 0. Between minus between minus 2 to 0, A of mod p equal to 1 minus p by 2, that is A of p, plus p, that is 1 plus p by 2, that is 1 minus mod p by 2. Between 0 to 2, A of mod p is equal to 1 minus p by 2 plus 0. So, 1 minus mod p by 2, and for p greater than 2, A of mod p. So, this is 0 and this max also returns 0. So, this is equal to 0. So, you can combine all these and write A of mod p is equal to max 1 minus mod p by 2 and 0. Because if you reduce mod p, if you increase mod p to say a value greater than 2, so this will become negative and therefore 0 will dominate over that. So, max will be 0. Similarly, here also max will be 0. Similar expression you can derive for the power law, this I leave on you as an exercise. So, just here what are the ranges in which you should divide? Minus infinity to minus 10, minus 10 to 0, 0 to 10 and greater than 10. Instead of 2 it is just 10. Till now we have seen that how to write the generalized coefficients and how different schemes fit a special case of this generalized coefficients. And we have seen that once you calculate the generalized coefficients, you can calculate even the dimensional coefficients like AE, AW. So, you can calculate AE from A of AE by D is equal to A of P, and AW by DW is equal to B of PW. So, the scheme may be that you first know what is A of mod P, from that you calculate A of P, and from that you can calculate B of P by using their respective relationships. Once you know that, that means you know AE by D and AW by DW, and AP is AE plus AW plus FE minus FW. This we have derived in one of our earlier lectures by giving the example of the central difference scheme. So, this you can show to be valid even for other schemes. So, you can calculate first the generalized coefficient, then the dimensional coefficients, and AE, AW, and then AP as a function of AE and AW, and that is how you can create the discretized equations. Okay. So, this is a fairly straightforward consideration for a one dimensional problem. What happens if we consider a two dimensional problem? In a one dimensional problem, remember the continuity equation was straightforward in a way that it just indicates that FE equal to FW. Now, for the steady state one dimensional problem that we have described. In a two dimensional problem, convection diffusion problem, the same concept can be extended. To extend it to a bit more general case, let us consider that the problem can also be unsteady. So, we are interested about the discretization of a two dimensional unsteady convection diffusion problem. So, what are the equations that we have? First of all, we must have the flow field satisfying the continuity equation. So, this is the continuity equation. Let us call it equation number 1, and the convection diffusion equation where Jx is rho u minus rho u phi minus gamma del phi del x, Jy is rho v phi minus gamma del phi del y. Let us consider the grid layout. Let us say that this is the control volume. So, we have the grid point P, its neighboring grid points are capital E, capital W, capital N, capital S, this is delta x E, this is delta x W, this is delta y s, this is delta y n, this is delta x, and this is delta y. So, this is your control volume. Now, we have to discretize the convection diffusion equation along with the continuity equation to get the corresponding discretized equations in 2 dimensions. That is our objective. So, let us begin with the continuity equation. So, what will be the first step? Integrate the governing differential equation. Remember, we are considering a finite volume discretization. So, integrate the governing differential equation over the control volume and also with respect to time. So, you have del rho del t dt dx dy okay. So, the limits of integration are from time t to t plus delta t, from x small w to small e, y small s to small n. As an example, let us consider a fully time implicit scheme for the time integration. So, if we first integrate this expression, it will be rho at time t plus delta t minus rho at t. We can make a profile assumption that rho is constant over a control volume, piecewise constant at each time. So it becomes rho p minus rho p 0, which is the rho p at the previous time, into delta x into delta y. Second term, so we can calculate this integral, it is rho u e minus rho u w, and that the next term will come as that integral of that dy. So we can say, we can combine these terms together, this along with integral of dy, to call this as integral of rho u dy for, or integral of dy you can simply write it at rho u e delta y minus rho u w delta y. So this we give it a name Fe and this we give a name Fw. So this plus Fe minus Fw into delta t. Similarly, what will be the last term? If this is Fe minus Fw, this is Fn minus Fs delta t, where we can define Fn and Fs as follows. What is Fn? Rho v n delta x, and Fs is rho vs delta x. So that is equal to 0. We can divide both the sides by delta t, so that we can ultimately get rho p minus rho p 0 into delta x delta y by delta t plus Fe minus Fw plus Fn minus Fs equal to 0. It is essentially an integral expression for mass conservation. So Fe plus Fn is the flow in Fe plus Fn minus Fw minus Fs is the difference of flow in and flow out, and that accounts for the change in mass within the control volume, which is the first term with respect to time. So it is an expression for the conservation of mass. We will stop here in this lecture and we will continue from this in the next lecture to calculate what will be the corresponding convection diffusion fluxes corresponding to the same problem. Thank you.